So, Claudiu Teodorescu, I representing the binary, and very happy to be here. Good morning, everybody. It will be a short presentation of WMI. I'll go over some of the information that I presented at Black Hat 2022, and then add 2 new attacks only for this, presented only at this conference. So, who is Binary? So, Binary is a startup in LA, focused on device security and monitoring threats below the operating system and see how they're moving up the stack into the operating system, kernel and user land, and then deploy their next level components. Unfortunately, Andrei and Igor, which contributed to this research, couldn't make the trip to LabsCon, but I'll take the credit for them and then maybe have a drink when we first meet in person. So let's go a little bit into the agenda. So I'll present touch a little bit brief on the architecture and features of WMI, just a primer for people that are not familiar with WMI, and also show some artifacts, forensic artifacts that I was deeply involved while reversing the format 5, 6, 7 years ago. Then I'll show how WMI is leveraged for firmware policy orchestration. And next, we're moving in actually the meat of the discussion on attacks on the WMI, how WMI is leveraged for evil, how we'll present a threat model, WMI threat model, and the different attack vectors, and then we'll move to present the 2 new attacks that I already advertised. So WMI architecture. It's a pretty comprehensive image, but in short, WMI is the Windows implementation of 2 standards, WBEM, which is web-based enterprise management, and the SIEM, which is a common information model. It's available system-wide in all operating systems and doesn't have to be installed, and it offers a standardized framework to produce and consume events that are represented as WMI objects. And in short, the architecture consists of the producers, WMI producers, which produce device telemetry as WMI objects, clients that consume those events to get device telemetry. One good example is PowerShell, which can be used to gather this type of telemetry both remotely and locally. Next is the SIEM standard, the common information model standard, which consists of the repository itself that stores the class definitions and namespace definitions, as well as persistent WMI objects. Then we have the MOF, which is an object-oriented language used to specify WMI artifacts to extend the standard. Next, we have the query language, which is the WQL. It's a SQL-like query to filter events. And DCOM and WinRM are used to remotely connect to transmit and receive data. And last but not the least is the WMI service, which is implemented as a services host DLL service in the NetSVCS group. WMI Providers, we already touched on this, just a little reminder. It's an instance of __Win32 provider, which is a standard class. Since providers are implemented as COM-based DLLs, they are identified by a class ID, and all the information of the COM is in the COM interface is in the registry. And in Windows 11, there are more than 4,000 built-in WMI providers. So one of the main ability of WMI is to act on events that cover pretty much any operating system event. And another ability that is is used in the wild by attackers is the ability to register permanent event subscriptions which survive system reboots. We'll see an example of that. There are 2 types of events, intrinsic events and extrinsic events. I left here the definition of both for future reference. Now, event filters specify which events should be transmitted to the bound consumer to act on those. The main properties of an event filter is the namespace in which it operates, the query language that is used, mostly the WQL, and the last but not the least is the query itself that specifies how to filter the events and send it to the bound consumer. And here we have the syntax, the general syntax of WQL for filtering, and then two examples. One is first is the intrinsic event example that triggers whenever Notepad.exe is launched. The other one is an example of extrinsic event, which monitors the run key for registry key for malware persistence. And now we talk about the consumers. So the consumer specifies the action that should be taken when an event filter triggers. And as we can see there, the standard defines already 5 or 6 default consumers to log files, to log events, to run scripts or command lines, or send notifications. And let's go a little bit more into detail. I mentioned the permanent event subscription. That's actually done for persistence and code execution. Is the method how you do it, and how you do it is just define the filter, which specify which event to trigger, the action that is defined by the event consumer, and then bind them into an instance of filter to consumer binding. So now let's talk a little bit about repository. So repository, it's the WMI repository. Its path and files can be found in the registry, and consists of 3 types of files. First is the index.btr, which is the index file for the WMI repository, implemented as a B3 on disk, and stores the search path strings in pages. Then is object.data, which consists actually which contains actually the namespace definitions, class definitions, and persistent WMI objects. And then again stored in pages and consisting of records. And then the last not the least is the historic versioning of three historic versions of mapping.map, which contains the mapping records, because in WMI there is abstraction logic to physical page, logic page number to physical page number. So the mappings are used to actually translate the logical page number to its physical correspondent. So let's look in practice how this should work. So we have the index.btr. First, we need to create the search path string for a WMI object that we're looking for. So that how it's done. You get the identifier for the namespace, class, and instance name. You concatenate them using some prefixes that are there mentioned. And then the index.btr is searched for that path string. And then the index record is identified. And what's important in that, the first number is the logical page number of the record we're looking for in object.data file. Then the other one is the record identifier. And the third one is the size of the record. So in order to do the translation, to find out where the physical offset is, we have to use the mapping map, which actually consists of 2 arrays of dwords, one for object.data, the other one for index.btr. And how it works, the logical number actually represents the index in the array. The value of that index, it's the correspondent physical page number. The same algorithm can be used for parsing the index.btr. It's a B3 on disk, as I said. So the format is using a logical page number for the pointers to the next nodes in the tree. And now knowing how we can parse the database, looking on a Lenovo system, in the root.wmi namespace, we found some interesting classes with Lenovo underscore prefix. And one of them is Lenovo BIOS setting. The other one is Lenovo set BIOS setting. And the third one is Lenovo set BIOS password. And if we're looking at the definition of Lenovo BIOS setting, we see that there is a property called the current setting, a type string that looks interesting to us. Doing a search on the repository for an instance of this class, we come up with empty results, which means those instances are not persistent. So they're generated on the fly by a WMI provider, which in theory should be provided by the BIOS vendor. Using PowerShell as a WMI client, we're looking for non-empty instances of this class, and then we're displaying when a non-instance we found a non-empty instance, we display the current setting property, and we have some information here. By magnifying on that, we get some interesting BIOS configurations about trusted execution, BIOS update, TPM, and so forth. So, what does it mean? We talked about getting and setting class instances, and there is a WMI provider that provides that information. So how does this work? So in the way, in this case, Lenovo implemented, so they provided an interface below the operating system that is implemented below the operating system, so the WMI provider calls on that interface to be able to read and alter this type of information. So pretty much from the user land, you have access to these settings that are very important for your computer. And from the management perspective or from firmware policy orchestration, this is a great feature because you can manage everything locally or remotely through WMI. But it's dangerous because in the last update from Lenovo, we have 2 CVEs that identify 2 vulnerabilities exactly in the interface that was provided for the WMI provider. And it's exactly for the set BIOS password. The SMI handler set BIOS password is used to actually complete the instance for the WMI set password class. So the WMI provider calls on that SMI handler to get the information and create the instance for the WMI set password. And as you can see here, these are industry-wide vulnerabilities. So WMI standard also provides a basic class to get some information about BIOS version, the vendor of your BIOS, and the device configuration. It's part of the standard, so it's Win32 BIOS. So now let's move to how WMI is used by mostly attackers, but also for defenders offers great flexibility in terms of providing device telemetry to security endpoint security solutions. But for attackers, offers a great living on the land infrastructure to do evil. And some of the ways WMI is leveraged is reconnaissance, AV detection, persistence, code execution, and so on. So that was from yesterday's presentation on Metador. Forgive my lacking skills of taking selfies. I'm not used to do that. But I saw here the WMI event subscription. So, and getting some more information from the talk, I divide a scenario how this can be implemented in WMI, which is very, very simple. You create a trigger that tells you that to execute the consumer whenever the system reboots, and wait a little bit for the boot sequence to finish, and then in the consumer, you just call the cdb.exe to debug the defrag.exe file. And to make the event subscription, permanent event subscription complete, you just need to bind the evil consumer to the evil filter that specify the trigger to the evil consumer that specify the action to be taken. Attacks on WMI. So this is the threat model. The threat model consists of a couple of components. One is the WMI service that communicates with WMI providers and consumers via ALPC, advanced local procedure called channels. Then we have the WMI files on disk, the WMI repository and the DLLs for the providers and more files and so on. Configuration in registry. And that's the data inside the WMI service. And on the right, there are the types of the attack vectors that can be used on this threat model. So if we have attacks on data inside the WMI process, attacks on pipes, connections, attacks on files and registries, sandboxing of the WMI using a user-land attack, and then using a kernel driver. At Black Hat, I already talked about this attack vectors, but today we'll focus on one more attack on data inside the WMI process, and actually showcase the attack on ALPC pipe connections. So most of the attacks on the data inside of WMI WMI service process, are done using this type of template, which is pretty simple. You have a global flag that is set in the initialization phase to its init value. And then when a consumer, when a new client comes in, a new request comes in, there is some dispatch routine that is called, and that flag is checked. If the flag is set to the required value, then the event is processed, and then no error, a success is returned. If it's not set correctly, then it drops the event and returns an error code. And we have here a list of flags that can be attacked and actually disable the WMI. Almost all of them I covered during my Black Hat talk. The M_PESC session is the one I'll cover today. And the one thing to mention, attacking those flags using the template provided before will disable WMI, but it will return different error codes. That's one of the things that happens. So let's look at the PESC session. So in the init function, a pointer to the interface IWMI DB session is set into that variable, which is a member of the C repository class. To note, there is a global object of the C repository class in the WMI DLL. So it's very easy to find this member. And then, as we can see in the shutdown method, we have the pointer is released. Then when a new WMI connection comes in, we have this call stack, and at the end we have get default session. When the get default session is called, that pointer is checked against null. If it's null, then a critical error is returned. If not, the ref count is increased on the pointer, and then no error is returned. So the attack is pretty simple. Set this member variable to null so that the function get default session returns the critical error. Now, the WMI attacks on ALPC channels. The items involved in this attack, the processes involved in this attack is services EXE, the WMI service, and the WMI consumers that interact with the WMI service. On the right, we have the kernel structures that are involved. So how does it work? From the services EXE perspective, a named connection port called NetSVCS is created by the services EXE and waits for a request from WMI service to connect. Once such request comes in, the services EXE allows the connection, and then the WMI service receives a handle to the client communication port, and the services exe receives a handle to the services communication port. And thus, the communication channel between services exe, the server side, and the WMI service, the client side, is established. The same thing, the same mechanism happens with WMI service and their consumers. Each consumer, WMI consumer, will have a channel to the WMI service to actually receive events that are produced by WMI providers. So the first attack is pretty obvious. We cut the cord by closing the handle on the client side. So this way, the targeted WMI client is not going to receive any WMI events. What he can do, the client can retry to reestablish the connection or restart itself. But the attacker app can act as a watchdog and then monitor the reconnection and then close the client communication port handle again. So time for the first demo. So we're launching command.exe. We validate that we have the latest version. We go to our main folder. We have two applications. One is the consumer, the WMI consumer receive WMI events. The other one is the attacker app. So the receive WMI events is just monitoring for new processes that are launched. So as you can see, multiple calcs, multiple notepads, and everything is logged into the WMI client. And now we run the attacker, and then we run the attack on the consumer, which is the client side. No events are generated, and then WMI client is disabled. Now we relaunch it again. And again, it can, because it reestablished the connection, the ALPC connection with the WMI service, it can get events back. We disable it again. So from this perspective, this is a different client, even if it's the same process, the same application. Yeah. So now again works. So now we attack the client side. The same attack can happen on the server side. So what we're going to do, we are closing the server communication port in the WMI service. Again, we're checking we have the latest version. We're running the WM tester, which is a way to interrogate WMI. So it is running. Now we do our attack, this time on the WMI service. No more events are received. Now try to restart. We cannot restart because the server side of the pipe has been closed. Cool. Going back. And now, conclusions. So WMI is created for performance monitoring and telemetry gathering. without security first in mind. That's one of the points that we want to make for this talk. We want to make sure that people are aware about risks that they can have if they rely on this telemetry. Yes, you can use WMI as a data point, but you should be able either, if you rely only on WMI, to detect this type of attacks, or use different data points and correlate them to get an idea of what's happening in your system. And as we saw, the attacks are very simple, because WMI has been designed for a different purpose. And one last thing that I want to leave everybody here, all this attack can originate in the firmware, which right now it's a big blind spot for the industry in terms of detection. Thank you very much, everybody.